Good afternoon, friends. Welcome to this seminar, and I must congratulate your teachers and your university for thinking about this disruptive innovation, if we can call it, that the students are at home, but they will not stop learning. So I am Dr. Ayan Datta from the Indian Association for the Cultivation of Science, which is the oldest research institute in Asia, and which is the only research institute in India which has given a Nobel Prize to India, which is the Nobel Prize in Chemistry. Nobel Prize in Physics, Dr. C.V. Raman in 1930, for the discovery of an effect which is now named after him, which is called C.V. Raman. So I'm going to talk to you again about light. Of course, Raman was all about light because he saw the bending of light and the breaking down of light into the Stokes and the anti-Stokes component. And now what I'm going to talk to you about is about a very new phenomena which has emerged in the case of organic chromophores, which is now understood now as singlet fission. So what is the typical case? What happens when a solar cell, all of us know how does a solar cell work. Solar cell works on an inorganic material. What you have typically is silicon. Silicon, as you know, is an indirect band gap material. Now, what is the band gap of silicon? The band gap of silicon is 1.1 electron volt, which is far too low to absorb solar radiation. So what happens in most of the cases, the light jumps from, when you shine light, the particles, the electrons, jumps from the valence band to the conduction band and jumps somewhere above the conduction, deep inside the conduction. Because the energy of solar radiation is more than the energy which is associated with the band gap of the system, which in this case is about 1.1 electron. Now what happens, this excess amount of energy has to be dissipated, and most of the time what happens, this excess amount of energy gets lost as heat. As a result, it causes 2-3 problems. The first problem is you are not able to harness the total energy of the solar system. Of course, we would like to harness all the energy of the solar radiation. You are not able to do that because the high energy radiations has been lost. The second one, of course, is you are creating a lot of heat, and heat is not good because that energy heat gets converted as disorder, and as a result, the devices lose their efficiency. Now, what else can be done? What else can be done is that if you can have a system in which you have, you are able to use, instead of a single radiation, you are able to use 2 radiations to reach the conduction band. This is what is called now as triplet annihilation, and this is something which we will talk about in some detail. Now, what I present to you is a typical case what happens in an inorganic system. So what happens in an inorganic system? You shine light, and of course the energy gets lost, and that energy gets wasted as heat. Now this is not something which is smart, and this is what happens for most of the inorganic systems like silicon, right? Silicon. Now think of something else where you can do something a little more smarter. And look at this. You excite an electron, and by the time that extra electron comes back to the minimum, you are able to use that excess amount of energy here to excite another particle from this ground state. Now, what you have resulted is this proverbial example of killing 2 birds with 1 stone. So as a result, you have created excitation in 2 different molecules which are lying near to each other by a single photon. So as a result, the efficiency of the process here is, how much is the efficiency? The efficiency is 200%, because you have been able to excite 2 particles by single radiation. Now, this is something which is a brilliant idea, and this idea is something which people are now working a lot to understand the efficacy and the process which is involved with this. So now what is happening? You are using a single excitation, a single electron, to create 2 excitation. As a result, a single high energy excitation is being converted into 2 low energy excitations, and as a result, you are able to excite 2 different particles. And this is what is called singlet fission. Why is it called fission? Because you are being able to excite two separate particles using a single photon. This is what is called singlet fission. So what happens for typically is that when photons are of energy which is higher than that of 2 to 3 times of the band gap, it is possible to use that excess amount of energy to excite 1 electron, using 1 electron to excite 2 different particles. And this process is used to excite another molecule or another electron in a molecule in the near vicinity of the system. And this process is called singlet. So I again show you what is the goal. Typically, when you shine light on a molecule, all the molecules are in their ground state, which is called the singlet state, and you shine a light. And when it gets excited, what you find is you are going to create two different excitations, which are triplet. You have been able to create two triplet excitations by shining one photon of light, which is called Singlet Fission. So what you have effectively done, you have created two separate triplets using a single photon, and this is what is called Singlet Fission. You have created two particles. Two particles have been excited using a single photon of light. Now, of course, this is of course an extremely efficient process for two reasons. First of all, as you know, if you are able to excite a system to its higher excited state S1, eventually some of the particles gets leaked to the triplet state by a process which is called intersystem crossing, which is a slow process, but it certainly competes with the original process. Now, here you have a state, or here you have a situation where you have been able to convert two different triplets, which are extremely fast, and I will show you why is it extremely. What happens in this case, if I am able to model the process, so what happens in this case, you have been able to shine a photon of light. You have created a local singlet excitation, and that local singlet excitation gets converted into two triplets. But remember, even if there are two triplets, the eventual spin multiplicity of the system is still one. So as a result, you have been able to preserve the spin multiplicity of the system before and after excitation. As a result, this is a spin allowed process. And because of this spin allowed process, you have been able to convert two separate triplets, and those two separate triplets are called singlet. So what you have resulted in this case is you have created what are called the alpha alpha and the alpha beta spins. As a result, the total spin state of the system is preserved. Now, what happens in this case? I can show you with a mechanism. So what happens in this case? Your molecules, you assume that all the molecules are in their ground state. The electrons are in their ground state, which is HOMO. You shine one photon of light, it gets excited, and it goes to the singlet state, which is S1, and that interacts with the ground state to create what is called which is called the two separate triplets, which is called the triplet excitation. The two different triplets. And you see the spin of the system still remains preserved, which is called the T1. You see, these are up, up, and down, down. So you have two different states which are preserved. Now, there is also a possibility that you can go through this process. You can either go to the S1, S0 state to the two different triplet state by two different mechanisms. Then you can have a two electron process where you can go to the S1 you involve two separate electrons in two different orbitals, or you invoke what is called the charge transfer state, in which the state, one of the electrons, one of these forms a cation and this one forms an anion, and through this charge transfer state, this forms what is called the coupled triplet state, which is called the triplet excitation. Now, as a result, there are two different possible mechanisms by which the process is occurring. One of them is called the two electron process, which is a direct process, and the other one is an indirect process, which is being mediated through a charge transfer. How does one control this state? Well, it is rather easy to control the state, that you can know which mechanism the process will go through, and it is typically done using a process by changing the polarity of the solvent, because if you're using a more polar solvent, you have a very high tendency to stabilize the charge transfer state. As a result, in that case, the process goes through this kind of mechanism. And of course, there are ways to calculate them. And what you calculate the two electron integrals, the two electron process, by calculating just the orbital overlap between the states. And from that, you can calculate the extent of electron coupling. And once you know the electron coupling, you can calculate the rate of transfer using what is known as the Marcus theory, through which you can find out the rate at which singlet fission occurs. And we'll look at it. Now, what happens in a typical case is when you excite a light, it goes to an excited state, it gets released, it gets relaxed, and then it gives you current. And this is a 1:1 process. As a result, this is not a very efficient one. And what happens in the case of a singlet fission, you create an excitation from the ground state to one of this higher excited state, and that splits into two different states. And those two different states form what is called singlet fission. And because of singlet fission, you can increase the efficiency of solar cells by as much as additionally more than 20%. So this is a very important finding, because then In that case, you can use solar radiation. Remember, solar radiation is one of the most efficient forms of radiation. It is almost free. You don't need to depend on fossil fuels. You don't need to depend on burning coal, and you don't need to worry about the side effects of pollution and other things. So singlet fission does have a very important role. Now, as it turns out, singlet fission does not occur by default for many systems. There are only very few systems which are known to show singlet fission. And what are the conditions for singlet fission for a molecule to be singlet fission active? The conditions are rather easy. First of all, you need to have the first singlet excitation, the S0 to S1. The energy gap should be such that there is a triplet state in between, which is exactly at half of the state. So that when you make an excitation from S0 to S1, it forms two separate triplets, and those two separate triplets get coupled. So as a result, the first condition is your singlet triplet gap has to be exactly half of the singlet gap. So there are very few molecules which satisfy this. And of course, the second condition is you don't need any other triplet state, say T2 or T3 in between the S1 state, because in that case, those two triplet states, T1, T2, can combine among themselves to again get back to the singlet state. So as a result, that process is going to compete with this. So this is what I'm trying to explain you. You have created a singlet excitation, and from the singlet excitation, you're going to form two coupled triplets. In other words, your singlet gap has to be exactly half of the triplet gap. And there are very few molecules which actually satisfy such a condition. What are the typical molecules which are known to show this kind of a singlet fission? One of the classic examples which does show this kind of an activity is a molecule called pentasine. Now, what is a pentasine? Pentasine is a molecule in which you have fused 5 benzene rings linearly. So you have one molecule, this is benzene, this is naphthalene, this is anthracene, this is tetracene, and this is pentasine. Now, pentasine is a molecule, one of the first classic molecules which is known to show singlet fission because its electronic states are favorably placed so that you can always have a triplet state which is exactly half of that singlet position. Now, this is what is example. For example, this is the case for pentasine. In pentasine, you have created an excitation, and that excitation splits into two different triplet states. So the S1 gap is exactly twice of the triplet gap. Now for tetracene, as it turns out, the S1 it does not have the right energy matching because the S1 is still lower than twice of that state, but S2 does, or S2 and S3 does. So of course, for molecules like tetracene, you need to excite the molecule to a next higher excited state, say in this case, an S3. So in this case, you have been able to create an excitation in a molecule, and these excitations are called singlet fission excitations, in which you create one local excitation in a molecule, and that creates excitation for two separate molecules which are close to each other. And this kind of excitation is what is called intermolecular singlet fission. Why is it called intermolecular singlet fission? Because you need two molecules which are in near vicinity, so that one local excitation in the molecule gets transferred to a nearby molecule, and you are able to create excitation in a pair of. Consider the case of, now there is another case which is called intramolecular singlet fission. And in the case of intramolecular singlet fission, you have a case where you create both the molecules are connected through a bridge, and as a result, singlet fission occurs within the same molecule. As a result, you have one molecule, you create a local excitation, you form the coupled triplets within the same molecules, and then those same molecules interact, and then they separate into two different. So now, as a result, you have singlet fission. There are two types of singlet fission. One is called intermolecular singlet fission, another one is called intramolecular fission. So now what I'm trying to tell you, there are two kinds of singlet fission: intramolecular singlet fission and intermolecular. Intramolecular singlet fission is the case where you have the fission occurring within the same molecule or within same parts of the same molecule in two different sections. Whereas intermolecular singlet fission is where you have the molecules which are physically separated from each other. What are the experimental techniques which you need to know? The experimental techniques which you need to know for singlet fission are, of course, you have to organic synthesis is required because you need to synthesize this molecule. You need to look at the absorption spectra, the fluorescence spectra, and the phosphorescence spectra, so that you know where are the T1, T2, and T3 states. And then you also need to know cyclic voltammetry so that you can try to find out whether there are charge transfer states or not. Also now, you should also do transient absorption spectrum, because by this, you will be able to know the singlet fission dynamics and the triplet quantum yield of the system. Consider the case. For example, a molecule like anthracene, we have already told you that anthracene does not satisfy the condition of singlet fission. Look at the case of anthracene. Now, anthracene here, of course, does not satisfy the condition because anthracene has a singlet state which is at 3.13 electron volt, whereas twice the energy of the triplet state is at 3.66 electron volt. So as a result, the singlet state is not higher than twice the triplet state. Now consider the case. Now how can you tune this molecule? You can tune this molecule using various techniques. One of them, if you substitute this molecule by an electron withdrawing group, you reduce this gap. But it is still, you see that the singlet state is still not come close to the triplet state. For example, this is a molecule like 9-cyanoanthracene, and 9-cyanoanthracene, you see, you have been able to reduce the gap to about 3 electron volt, whereas this was about 6 electron volt, 0.6 electron volt, and this was 0.3 electron volts here. So as a result, you can tune the interactions within the molecule, and as a result, effectively change the level of the states between the singlet and the triplet. Now, consider the case of the molecule. For example, this is the energy level of the singlet, and this is the energy level of twice the triplet. I mean, this is the energy of the twice the triplet, and this is the energy level of the singlet. You see, as you go from benzene to naphthalene to anthracene to tetracene to pentacene and so on, only after tetracene you get to see that the twice the triplet state, the energy comes down than the singlet state. So as a result, a molecule, so the only molecule which is going to be suitable here is this molecule here. In this case, molecules after pentacene are going to be suitable for molecules like this. Now, are there new molecules which we can predict? Well, as it turns out, you can actually you can find new molecules. For example, if you are able to dope the system or you want to substitute the carbon by silicon, you can see a molecule like this, the 9-sila anthracene, that of course has going to form the singlet state, which is lower than the triplet state, even at a lower level. So as a result, by substituting atoms like carbon by silicon, you are able to get to a state which is much lower in energy, and yet you are going to get new molecules. In other words, 9-sila anthracene is predicted to be the smallest molecule that satisfies the primary condition for singlet. And of course, you can also tune this and you can make the energy difference between the singlet and the triplet as close as zero. For example, you are going to substitute groups here. When you substitute groups here, for example, you have a 9-cyano 10-cyano 9-sila anthracene that has exactly the right energies. In fact, this is one of the smallest molecules which has been designed in our lab, which is predicted to show singlet. In fact, we are competing with the group of the Nobel laureate Roald Hoffmann, because Roald Hoffmann has been also looking at some of these molecules, but Roald Hoffmann has suggested a molecule like this, which is a boron substituted charge transfer mediated compound, and our molecule is the next smallest system to that. Of course, our molecule is much better in a sense because we have not substituted any other atoms other than only one silicon in the carbon, whereas he had to substitute 4 atoms, 1 boron, nitrogen, boron, and nitrogen. So of course, in other words, we have been able to design, we have been competing with molecules. In fact, this is a kind of a Guinness Book of World Record, like we are trying to find out molecules which are small, molecules which can be designed in a laboratory, which can show singlet fission, which are not the natural ones. Why do we want new molecules? We want new molecules because we want to work newer devices. We want to study newer systems, right? Now, consider this. Now, what happens in the case, for example, a molecule like this? You're able to also control systems like by controlling the level of interaction between the systems. For example, this is a molecule like 9-phosphoanthracene. For example, this molecule like this, depending on the molecule of packing or the molecule of interaction. For example, this molecule is known to undergo 2 different modes of packing. And depending on the nature of packing and the nature of interaction between the molecules, you are able to control the states, you are able to control the rate of phosphorescence, you can control the rate at which intersystem crossing occurs, and then depending on the nature of packing between the molecules, you can control the spin-orbit coupling between the S1 state and the other triplet state, and as a result, you can control which state would have higher efficiency of intersystem. Now, of course, these are little details. The reason why I mention these details because this is a very typical way to calculate it. But you need to do, for example, these are molecules which have sort of charge transfer character. Handling molecules which have charge transfer character is little non-trivial, because what you need to worry about in this case is to study the interactions between the molecules. And what people do now is to use what is called the range separated DFT methods, which is called the range separated DFT functionals. Through this, people are able to calculate this kind of thing. Now, what we have been able to show that you can go, depending on the mode of interaction and the way the molecules pack, you can actually control the extent of interaction between the two, and all of them show what is called the Alside rules. Follow the Alside rules, and what does the Alside rule say? Alside rule says that all these kind of transitions, I mean, fast intersystem crossings are allowed for states in which there is a change in the overall angular momentum. For example, if you are able to change the orbital type or the nature of interactions between the states, you are able to control the nature of interactions between. Now consider the case, our first molecule, which is 9-cyano, 10-cyano, 9-silaanthracene. Now this molecule is known to undergo packing, and depending on the nature of interaction, you can see that there are various modes of packing between the molecules. And you see there are various configurations within the molecule. And depending on the favorable configurations between the molecule, you are able to design which molecule is going to effectively interact with. For example, you see this molecule, depending on the two various modes of packing between the molecules, whether they are packing like this or they are packing like this, whether it is a herringbone packing or whether it is a pi-pi stacking packing, you are able to control the nature of interactions and the efficiency of Singlet fission. And once you know this, you can actually calculate and fit it into a master equation, very simple equation, in which you can go through a direct process or through an indirect process, a one electron process or a two electron process. The one electron process is mediated through a charge transfer state, whereas the two electron process is mediated through this state. I mean, both the processes are occurring together, and you can show that based on this, whether you have a charge transfer state, you can work on a kind of a consecutive reaction, a model for a very simple consecutive reaction. You can find out the rate of process, a rate of Singlet fission, and you can see depending on the mode of packing. For example, the first configuration has an efficiency of 198%, whereas the other one has an efficiency of only 25%. So, depending on the same molecule under a different packing orientation, does show different kinds of Singlet fission efficiency. So the idea is to kind of design molecular packing in which the molecules are designed in a very specific particular orientation, so that we are able to show very large Singlet fission. Now, as I'm trying to tell you, depending on the mode of packing of the molecules, you're going to see Singlet fission efficiency. And this is exactly what we have seen for a molecule. This is called TIPS anthracene. This is called triisopropyl silane anthracene. This molecule crystallizes in two different crystal structures. So these are two different crystal structures for the same molecule, which is of course which we know is called polymorphism. The same molecule crystallizing in two different space groups. And then based on these two different space groups for the same molecule, what we have been able to show that the nature of interactions of Singlet fissions are different. As a result, the orbitals which are involved in those transitions from going from the singlet to the singlet state and the singlet to the triplet state are different. You see, depending on the modes of interaction, you see that the P1 and the P2 states, they have different Singlet fission. So that's a very good news for us, is because we have been able to show that the nature of interactions between the two states depend on the method of depend on the mode of packing between them. So you not only need to design the molecule which has the right states, the molecule which has the gap, the first singlet gap exactly needs to be twice the triplet gap. You also need to control the nature of interaction between the molecules, weak molecular interactions, weak intermolecular interactions, typically hydrogen bonding, dispersion, or pi-pi stacking. The other very important thing is, apart from the fact, for example, this is a molecule which is a very well-known molecule, it's called pentacene. And this molecule pentacene crystallizes again in various groups, various space groups. Now, depending on the fact that whether you have 4 phenyl groups which are connected to pentacene or 2 phenyl groups, the nature of efficiency between this of singlet fission gets controlled significantly. For example, the same molecule has different, I mean, whether you have pentacene, whether you have diphenyl pentacene, or you have triphenyl pentacene, the efficiencies are different. And because of these efficiencies, the nature of interactions between the molecules are also. What we have been able to show that depending on the nature, whether you have tetraphenyl pentacene or a diphenyl pentacene, the nature of interaction, the interactions which control the molecule, they get controlled and they effectively tune what is called the interaction between the systems. And of course, you can see a molecule like tetraphenyl pentacene and a molecule like diphenyl pentacene, they have different kinds of packing. For example, this is a slip stack parallel arrangement where this is a herringbone pack. So depending on the packing, you can have different modes of interactions. And these modes of interactions control the efficiency. For example, for triphenyl phosphocene, for triphenyl example of pentacene, this molecule gets excited to the form of an excimer, whereas for a diphenyl, for example, for a diphenyl pentacene, this occurs through the process of what is called super exchange, in which they hops from one end to another. So the nature of interaction between the molecules does get. Now, what we have shown you till now, we have shown you in examples, all the examples we have. What we have are examples of intermolecular syndication. Now, what I'm showing you now here is an example of intramolecular syndication. For example, you create an excitation in the sulfur end of this molecule, and once it creates an excitation, that splits into two different ends. As a result, you have an example of what is called intramolecular singlet fission. And again, the specific mode of interaction in which this excitation occurs, that becomes very critical, because if you are going to excite to this vibrational mode, only on this typical vibrational mode, these states will interact. Otherwise, for the other mode, those states do not interact. So this is the point which we are trying to make, that we can show that typically for the states where you have a single donor, this is a donor end, whereas two different acceptors which are identical, you are going to interact, and particularly the mode in which they interact, they become very critical. What I have been trying to tell you for this time, what I'm trying to tell you is we can design molecules. We can design molecules which have the right states and the right energies, so that they can be excited, and from those excitations you can create a library of molecules which can be of very important technological. What we have shown here, in fact, this is a feature article which appeared from our group in the Journal of Physical Chemistry, where we have shown that you can excite molecules, and you can excite molecules in such a way that you are going to create singlet fission in the molecule, and you can design molecules which have the right orbital symmetries, so that you can create the right excitation within the same molecule. So idea is we can use computational methods to design new molecules, which have the right symmetry and the right states by which you can make new and exciting systems. In fact, this appeared in the 15th August issue of the Journal of Physical Chemistry as a feature article. So now, of course, I thank the ACRB, the Department of Science and Technology, for funding this project. I thank my students, Dr. Kalishankar Bhattacharya and Dr. Arun Pal, who have helped us in a very significant way in doing this calculation. I also thank Professor Manoranjan Kumar, with whom we had discussed a lot about some of them. And I thank you all for being patient and for listening to my lecture.
Meantime, and actually, the moment you are saying that it all depend upon the designing of the molecules, and a single photon can excite the two electrons. If there is any effect, suppose my chain length is the larger. I am designing the molecules, and my chain length is the larger. So in that case, do we have the something which can help us, or something which can basically affecting the excitation of the electron in that manner?
Yeah. So, for example, the chain length is very important because you need to control the electronic states to know the energy levels of the system. For example, if you need the triplet, for example, singlet fission will occur only when the triplet state is exactly at half of the energy of the singlet state. So you need to tune the states. For example, if you have very large conjugation, what will happen? Typically, higher energy triplet state will fall below the singlet state. So that would be detrimental to the.
Apart from that, suppose you have the some material. Generally, the people go for the this organic semiconductor. they go for the multi stacking structure, they go for the multi-layer structures. So suppose if the interface of the one material, say you are talking about the pentacene, and you have modified the pentacene with that one. So in that case, if you modify pentacene, how much it will be going to interact with another layer? Say it is the LQ3. So in that case, is the excitations will be affected because dielectric material can stop such kind of the excitation and the efficiency can be changed.
That is right. For example, if you have, let's see, this is the layer that this excitation is generated, but that excitation has to be transferred to the circuit out. So if the molecule and the surface interacts very strongly with the leads which is connecting, that is again not going to be good. So idea is to design the molecules. I mean, this works typically for organic molecules. So the idea is to design small organic molecules which can show this kind of efficiency to a very large extent.
So using such kind of technique, can we also design the perovskite material which can give the double excitation by the single photon?
That's right. But for perovskite materials, you typically use heavy elements. Now, when you use heavy elements like lead or mercury or barium, so they already have very strong spin orbit coupling effects. You want, because if you have spin orbit coupling effects, that would immediately show phosphorescence. We want phosphorescence not to compete with fluorescence, because this is completely spin allowed.
There is one question of student Sanu Maji who is doing his 6 month dissertation training in Canada, Quebec, Canada, and he is asking, like if we can design such molecules, then how much efficiency we can expect from such molecule best for solar cell.
Right. For example, this would increase the efficiency. Typically, efficiency of solar cell is about 33% maximum. This is theoretical. Now, by this, you can go in principle up to 55%. So, in principle, you can go up to, you can additionally go up to 20%.
Even the moment we are saying that the two spin will be excited, two electron will be excited due to the several other regions, efficiency will be not go the double. It will be around 20% enhancement in the solar cell.
Overall, I
Overall.
mean, in principle, the efficiency seems like 200%, but then you see, not all of them would be useful. Even 20% enhancement is very significant.
Yes, yes. Because nowadays the perovskite solar cell is giving the efficiency of around 47%. And if we go for the organic solar cell, people are still struggling around 10% to 12, 13%. So even if the 20% enhancement is coming, it will be going to be around 15 to 16%, and which will be almost, you can say, that based upon the commercial silicon solar cell, will be about to that one. 16-70% efficiency is also good because the polymeric materials or the organic solar cells are the cheaper if you go for the mass production. So I think that is a very good concept which people, the chemist can execute. They can think of by this way, and they can plan for such material.
Can this molecule be functionalized with graphene-like materials, and change the property or enhancement of efficiency, etc.? Can it
Yes.
be possible?
So people are trying to do this, for example, because you see, these small molecules already have polyaromatic hydrocarbons. You see, benzene, naphthalene, anthracene. So they have this kind of effects. So people are trying to use this kind of on graphene fragments to see if you can expand the solar cell.
And can it be possible to functionalize with any other semiconducting materials so that its efficiency can be changed? I'm not telling that increase or decrease. Can we play around with this kind of molecules functionalized with any semiconductors?
Right. So we have people are this is a very active area of research. People are trying to design a lot of tune these effects to get newer kind of interactions like graphenes and other semiconductors, silicenes and boronitrides.
So a lot of things can be done in this area.
Yes.
So the another question is how stable is the such molecules?
Yeah. So these molecules are pretty stable. For example, I mean these are these are typically polyaromatic hydrocarbons, and these substituted polyaromatic hydrocarbons are stabilized. The idea is to get them in the crystalline form. That is an effect. because these crystals have to be grown, and that is the challenge. You can make these molecules. These molecules are stable, but these effects need to be at the solid, because otherwise the molecules will not interact.
One problem with the organic solar cell is the stability. So
That
how
is right.
stable can be such molecule-based solar cell will be stable?
That is right. For example, these organic materials have this problem of stability, particularly because these molecules can become very ear sensitive. Particularly when you have heterosubstituents, for example, silica and germanium. If you dope into it, by the way, this is the same problem which is there for silicons, for two-dimensional silicons. I mean, metallic silicon is silicon is a very stable element. You can create big crystals out of it. But atomic silicon, if you have few atoms of silicon within a molecule, they are very unstable. And we have seen this for silcenes, germanies, black phosphorus, phosphorine. So many of these inorganic analogs have of organic molecules have instability.
Is there any possibility that we can make such chemical compound who is good for solar cell as well as they are transparent in the nature?
So this is a very important issue, and many of these molecules are not transparent. So that is also one of the issues. So how to make transparency for these molecules? Maybe to put it in a kind of a matrix of polymer which is transparent, and then to make islands of small islands.